This is a screencast from the Motion, Forces, and Energy textbook. We're going to start with satellite motion. You do need the note sheet that goes along with this, so make sure you get that. Objects that orbit Earth are satellites of Earth. Satellites go around Earth in nearly circular orbits, with the centripetal force being gravity. If gravity is pulling satellites toward Earth, why doesn't a satellite fall to Earth like a baseball does? Actually, a satellite is falling to Earth just like a baseball. Suppose Earth were perfectly smooth with no mountains or hills. Imagine you throw a baseball horizontally. Gravity is going to pull the baseball downward so it travels in a curved path. If the baseball is thrown faster, its path is less curved and it travels farther before it hits the ground, as shown in Figure 11. Which is over here. If the baseball were traveling fast enough as it fell, its curved path would follow the curve of Earth's surface. Then the baseball would never hit the ground. Instead, it would continue to fall around Earth. Satellites in orbit are being pulled toward Earth just as baseballs are. The difference is that satellites are moving so fast horizontally that Earth's surface curves downward at the same rate that the satellites are falling downward. The speed at which an object must move to go into orbit near Earth's surface is about 8 kilometers per second, or about 29,000 kilometers per hour. To place a satellite into orbit, a rocket carries the satellite to the desired height. Then the rocket fires again to give the satellite the horizontal speed it needs to stay in orbit. Now we're going to talk about air resistance. So whether you are walking, running, or biking, air is pushing against you. This push is air resistance. Air resistance is a form of friction that adds to slow down any object moving in the air. Air resistance gets larger as an object moves faster. When an object falls, it speeds up as gravity pulls it downward. At the same time, the force of air resistance pushing up on the object is increasing as the object moves faster. Finally, the upward air resistance force becomes large enough to equal the downward force of gravity. When the air resistance force equals the weight, the net force on the object is zero. By Newton's second law, the object's acceleration then is zero, and its speed no longer increases. The constant speed a falling object reaches when air resistance balances the force of gravity is the terminal velocity. That is the maximum speed. Okay, now we're looking at air resistance and shape. The amount of air resistance depends on the object's shape as well as its speed. Moving at the same speed, the air resistance on a pointed, narrow object is less than on a broad, flat object, such as a leaf or a piece of paper. A falling skydiver is in a spread eagle position, wide arms open, as shown in Figure 12a. Might reach a terminal velocity of about 200 kilometers per hour. But with the arms tucked downward and the legs closed, air resistance is less, and the diver might reach a terminal velocity of over 300 kilometers per hour. When the skydiver opens the parachute, the force of air resistance on an open parachute is so large that the skydiver's terminal velocity quickly is reduced to about 20 kilometers per hour. And this concludes this lesson on air resistance. Thanks for watching.